Thanks for joining me for our second tutorial. In today's tutorial, we're going to review the goals of modeling. We'll also introduce multiple linear regression, including adjusting for confounding and interpreting adjusted and unadjusted results. And finally, we're going to discuss how to compare models. The goals of regression can be broadly placed into one of three categories. First is descriptive. Here, we are simply attempting to describe relationships or patterns that may exist. We are not interested in making any sort of predictions. We are only interested in examining the direction of associations that might exist. With predictive models, our goal is to build a model that's good at making predictions for the outcome. We still need to have a good reason to include explanatory variables in our model, but the ultimate goal is to build a model that is good at predicting the outcome. So we want to include all predictors of the outcome. With comparative or hypothesis testing models, we want to compare two or more groups, populations, or treatments. So the focus is on a single explanatory variable, but we include other variables in our model to control for confounding, so that we get the least biased estimate of the relationship between X and Y as possible. And the majority of health studies are comparative. Multiple linear regression is used to relate two or more explanatory variables to a single quantitative outcome variable. The regression equation is shown at the top of the slide here. The interpretation of the intercept and slopes is similar to simple linear regression, except that the intercept now refers to the mean value of y when all x's equal 0. And the slope of each explanatory variable represents the mean change in y for a 1-unit change in x, holding all other x variables constant. As I said previously, most health studies are comparative, where we want to look at the independent relationship between a single x variable and y. Multiple linear regression allows us to control for known confounders that may distort our estimate of the association between x and y. For example, we could be interested in the effect of smoking on lung capacity, but the smoking and non-smoking groups might differ by characteristics other than smoking, like age and gender. These variables may act as confounders, distorting our estimate of the association between smoking and lung capacity. Including these confounding variables like age and gender in a multiple linear model will tell us the relationship between smoking and lung capacity adjusting for age and gender, which means holding age and gender constant. The explanatory variables in a multiple linear regression model can be either continuous or categorical. If your x variable is continuous, your slope tells us the mean change in y for a 1-unit change in x, holding all other x's constant. If your x variable is categorical, the slope tells us the mean difference in y between the two groups of x, holding all other variables constant. So let's turn to an example. Our research question is, what is the relationship between traffic density and measured levels of carbon monoxide on the San Diego freeway? Let's say we run a simple linear regression model, and this is our output. How would you interpret the intercept and slope for traffic density shown in the output? Our slope tells us that for every increase of 1 vehicle mile in traffic density, carbon monoxide increases by an average of 0.0208 ppm. Our intercept tells us that if traffic density equals 0, we would expect a carbon monoxide concentration of 1.219 ppm. If we know that wind speed has an impact on CO concentration, we may want to control for this in our model. I don't actually think vehicle density is associated with wind speed, but we'll continue with the example for demonstration purposes. So let's take a look at our results. Our interpretation for traffic density, our explanatory variable of interest, would be for every increase of 1 vehicle mile of traffic density, CO concentration increases by an average of 0.0183 ppm, controlling for wind speed. Our p-value associated with traffic density is less than 0.05, so we should reject the null hypothesis that the true slope for traffic density when controlling for wind speed equals 0, and have evidence to suggest that the slope does not equal 0 when controlling for wind speed. The interpretations for the intercept and wind speed slope are also shown here, but our research question was about traffic density, so we wouldn't normally interpret these. Let's say we also decide that we want to control for daylight. What would our interpretation be now? Our interpretation of the traffic density slope would be, for every increase of 1 vehicle mile of traffic density, CO concentration increases by an average of 0.0168 ppm, controlling for wind speed and daylight. Our p-value associated with traffic density is less than 0.05, so we should reject the null hypothesis that the true slope for traffic density equals 0 when adjusting for wind speed and daylight, and have evidence to suggest that the slope does not equal 0 when adjusting for wind speed and daylight. Whenever you're asked to interpret coefficients, remember to always list the variables that you're adjusting for. And also remember to pay attention to the p-values, which tell you whether or not you should reject or fail to reject the null hypothesis that the slope equals 0. As I mentioned in the last tutorial, it's critical that you understand the data that you're working with in order to correctly interpret the output of your regression model. So for example, you need to know the units of measurement for both your explanatory and outcome variable in order to correctly interpret your findings. For example, if you're looking at body weight, is this measured in kilograms or pounds? It's also important to know the coding of your categorical variables. In the previous example, looking at the association between traffic density and levels of carbon monoxide, we controlled for daylight, which was a categorical variable, daytime versus night. So is your reference group daytime or nighttime? We had said that nighttime equals 0 and was our reference group, and daytime was our category of interest. But it's important to know the reference group that your software is using. Binary categorical variables are typically coded as 0 and 1, and 0 is usually automatically treated as the reference group. But you can also recode your variables to change this. So for example, if you wanted daytime to be the reference group in the previous example, you could recode the categories of the variable in R to do this. So just a quick recap. What is a confounder? A confounder is a factor that distorts the estimated measure of association when the primary exposure of interest is mixed up or stuck together with some other factor that is associated with the outcome. The criteria for a confounder is that it is a factor that is associated with both the primary exposure of interest and the outcome of interest and is not on the causal pathway. It must meet all of these criteria in order to be considered a confounder. For example, let's say we're interested in the association between physical activity and heart disease, and we're wondering if we should adjust for fluid intake in our model. People who are more physically active may drink more fluids than inactive people, so the potential confounder is associated with our explanatory variable, but drinking fluid likely has little to no effect on the risk of heart disease, our outcome, so fluid intake is not a confounding factor here, so we should not adjust for it. As another example, let's say we're interested in the effect of injection drug use on HIV incidence, and we're wondering if we should adjust for syringe sharing. Syringe sharing is associated with injection drug use and is a predictor of the outcome, HIV incidence. But syringe sharing is on the causal pathway between injection drug use and HIV incidence, so we shouldn't adjust for it in our multiple linear regression model. So it's really important to make sure that a confounder makes sense conceptually, not just numerically or statistically. So let's go over an example. Let's say we're interested in the effect of smoking on FEV, but we want to know if age is a confounder. Conceptually, it makes sense that age could be a confounder. It could be associated with smoking status, so smokers could be more likely to be older, which we saw in our bivariable analyses in the last tutorial. And we also saw that FEV tends to increase with age. It also wouldn't make sense for age to be on the causal pathway between smoking and FEV. So conceptually, it makes sense that age could be a confounder. We then want to see if age meets statistical criteria for a confounder. One way to do this is to first estimate a simple linear model that includes only smoke. Here we can see that the slope for smoke equals 0.71, which means that smokers have an FEV that is an average of 0.71 liters greater than non-smokers. To check if age confounds the association between smoke and FEV, we can add age to our model. We compare the results of our original simple linear regression model with our multivariable linear regression model that includes age. we are interested in two things: our change in the estimate of the slope associated with smoke, and our change in the estimate of the standard error associated with the smoke slope. As a rough guide, if there's a change in beta 1, the slope for smoke, by greater than 10%, the new variable, age, is a confounder. If there's no change in beta 1, but the standard error goes down, then the new variable is a predictor, meaning that it is a predictor of the outcome, but is not associated with our explanatory variable of interest. If the standard error of beta 1 increases a lot, then the two variables are collinear. Collinear is another way of saying that the variables are very highly correlated to the point that they're basically measuring the same thing. This can cause major problems in your multivariable model. If a variable is a confounder, you'll want to keep it in the model to adjust for its confounding effects. What about if a variable is a predictor? The answer is that it depends. If you have a predictive model, you'll always want to keep a predictor variable in your model. But in a hypothesis testing or comparative model, it depends. If it's age or gender, or it's shown in the literature to be important, then you'll probably want to keep it in your model for face value. And also, including predictors in your model can improve the precision of your estimate of interest. So your confidence intervals for the slope of interest will be narrower. But we don't want to keep too many variables in our multiple linear regression model. This leads to what's known as overfitting. Overfitting actually gives you less precise estimates and makes the model too specific to your data set, which reduces the generalizability of findings to your study population. What about if two variables are found to be collinear? If two variables are collinear, you will want to drop one of these variables from your model. Usually this is the one that you think is the least important, which will depend on your topic area. We'll talk more about collinearity in a second, but for now let's return to our example. So going back to our original model, how did adding age to our model affect our slope for smoke? Do you think age is a confounder, another predictor of FEV, or collinear with smoking? The estimate of the slope for smoke changes substantially. So the direction of the association actually changes from positive to negative. So age appears to be a confounder of the association between smoking and FEV and should be kept in our model. In our second model that controls for age, our beta 1 is interpreted as smokers have an FEV that is an average of 0.21 liters lower than non-smokers, adjusting for age. So what is collinearity? As I mentioned, collinearity occurs when two or more explanatory variables in a multiple linear model are highly correlated. This is similar to confounding, except that x1 and x2 are so highly correlated that they can't be separated. So this really distorts estimates in your model since the two variables are essentially sharing the same effect. To assess collinearity between two variables, for example, age and height in children, you can examine correlations between the two variables. But the problem is that sometimes two variables aren't collinear until they're in a third model. So instead you could regress each explanatory variable on the rest of the other explanatory variables, obtain the R-squared for each model, and examine if the R-squared is large. If it is, there are a couple of ways to deal with collinearity. The first is to drop one of the variables. Another technique for dealing with collinearity is ridge regression, but we won't cover that in this course. Collinearity is the biggest concern if it involves the primary explanatory variable of interest, but it's less concerning if it's between the other x's. If two variables are collinear, how do you choose which variable to keep in your model? It could be based on prior subject knowledge or previous research about which variable is more important or widely known in your field. It could be based on how your variables are measured, so maybe one measure is known to have better sensitivity and specificity than the other, or maybe including one measure better meets the assumptions for multiple linear regression. And you could also compare the fit of the models with each variable included separately and keep the model that is a better fit. So let's talk a bit about assessing model fit. As we talked about last week, the R-squared is the proportion of the variation in the data that is explained by the model. In your multiple linear regression output, you'll see an adjusted R-squared. This takes into account the number of explanatory variables in your model. Whenever you add explanatory variables to your model, the R-squared will always go up, even if just by a little bit, even if a variable is not really that important. So adding a variable to your model will always increase the R-squared a bit just because of chance association. So the adjusted R-squared accounts for that. It's basically the R-squared minus a penalty for the number of x's in your model. An important thing to note is that we cannot use the R-squared to compare model fits. And the reason for this is, as I said, the R-squared will always increase when we add more variables to our model, even if these are useless variables. So we shouldn't use the R-squares of models to determine which model fit is better. Also, the R-squared describes how the model predicts the data, but we use the data to predict the model. So it doesn't really make sense to use this to compare models. So how do you choose the best model then? There are two methods that we will discuss. The first is the partial f-test. This test uses ANOVA to compare nested models and tells us if we can add or drop an explanatory variable from our model without increasing the sum of squared error. The partial f-test uses ANOVA to compare nested models only. A reduced model is a model that uses a subset of the x's from the full model. So the reduced model is nested within the full model. So for example, a model with smoke as the only x variable is a reduced model that is nested within a full model that includes smoke and age as explanatory variables. With the partial f-test, you're essentially comparing the full and reduced models to see if there is a statistically significant difference in the sum of squared error of the two models. To compare the two models, we want to compare the sum of squared error. Does the full model have a significantly lower sum of squared error than the reduced model? In other words, does the full model explain more variation compared to the reduced model? Are predicted values closer to the observed values? So what are the hypotheses for the partial f-test? The null hypothesis is that the sum of squared error of the full model is equal to the sum of squared error of the reduced model. The alternative hypothesis is that the sum of squared error of the full model is less than the sum of squared error of the reduced model. In other words, that the full model is better. By better, I mean the full model explains significantly more variation than the reduced model. Our predicted values are closer to our observed values. If this is true, then the F statistic should be large. This is the formula used to calculate the F statistic for the partial f-test. The F statistic is the sum of squared error of the reduced model minus the sum of squared error of the full model divided by the change in the parameters, or the change in the number of coefficients or slopes in your model, over the mean squared error of the full model. As a rough guide, with an F statistic over 4, we can reject the null hypothesis. So here's the output for the partial f-test comparing our two models. The F statistic is 793. Since the p-value associated with the F statistic is less than 0.05, we can reject the null hypothesis that there's no difference in the sum of squared error between the models and conclude that we have evidence to suggest that the full model is better. The full model explains significantly more variation than the reduced model. The second method for assessing model fit is to use the AIC or BIC. Both the AIC and BIC measure how well a model fits and penalize for more explanatory variables. The BIC just penalizes more harshly for the number of parameters. The main advantage of using the AIC-BIC to assess model fit is that the models do not necessarily have to be nested like they do with the partial f-test. The AIC and BIC can be used to compare nested models, but this is not necessary. These can compare models with entirely different sets of explanatory variables. So for example, you could compare a model with a categorical age variable to a model with a continuous age variable. In R, you simply fit your two models and use this code. The model with the lower AIC or BIC is the better model. Because AIC and BIC are measures of unexplained variation, a lower value means the model fits better. Neither the AIC nor the BIC can be used to test significance of a model. They are used only to compare competing models. The actual value of the AIC and BIC are not important. They do not have a numerical interpretation. It's more relative to the other model that you're comparing to. The lower the AIC and BIC, the better the model is. For nested models, the partial f-test and AIC or BIC should agree. So we're just going to conclude this tutorial with a summary of sources of bias. Recall that there are several types of bias in your model. Systematic bias is related to the study design and results in distorted estimates, but you can control for this with a good study design. Uncontrolled or residual confounding is another source of bias. This could mean that we aren't controlling for an important variable that is biasing our estimate of the association of interest. Interaction or effect modification means that the effect of x1 varies by or depends on values of x2. And we'll talk more about this as we progress throughout the course. And finally, collinearity is another source of bias, which I've said means that x1 and x2 are highly correlated. It's really hard to control for all of these factors in a study, but we want to get the least biased results as possible. Remember that all models are wrong, but some are useful. In the next tutorial, we'll move on to a new data set to recap multiple linear regression, including confounding and collinearity. We'll also go over effect modification or interaction, how to choose the best model, and the steps for fitting a multiple linear regression model.